Hello everyone, welcome back to Physics 331. Today I want to continue with our discussion of the Fourier series using complex exponentials. And this video will be a pretty short one. I just want to go through an example to show how we can actually use this. And we're going to do a simple example. It's going to be the square wave. And what we're going to try to show is that when we construct the Fourier series using this complex exponential form, we will recover the same result that we had using the previous Fourier series in terms of the trig functions sine and cosine. So last time we went through derivation of the Fourier series in terms of complex exponentials, and what we established is that any periodic function of time can be expressed as this infinite series. The sum from n goes to from minus infinity to plus infinity of a coefficient Cn times e to the I n omega t. So what we need is a way to calculate those coefficients Cn, and that was determined in this way. So we take the integral over one period of the periodic function f of t multiplied by e to the minus I n omega t. Okay, so let's see how this is going to work in practice. As I said, what we're going to do is we're going to use a square wave. So this will be our time axis, and here will be f of t, and our function will go between plus 1 and minus 1. So here's plus 1, then it drops down to minus 1, and it just repeats this over and over again. And so here it would drop down to minus 1. Okay, like so. So here is 1, and here is minus 1. And so let's just pick for our axes. This is, remember, capital T was half the period, and so capital T is this length. So here is t, here's the full period is 2t, here's 3t, 4t, and so on. And here's 0, minus t, minus 2t, and so on. Okay, and so what we want to do is we want to calculate the Fourier series for this square wave in terms of the complex exponentials. And really what that amounts to is finding these coefficients Cn. So there's our Cn expression above. So Cn is going to be 1 over 2t. And what we'll do is we'll split our integral into two pieces. We'll start with the minus t to 0 range. And we can see over that range our function f of t is just equal to minus 1. So f of t for this range of times is minus 1, and then we multiply by e to the minus I n omega t, integrate over time. And then we have to integrate over the second half of the period, and so we'll go from 0 to plus t. Over this range of time, the function f of t is plus 1, so f of t is just plus 1 for all of these times, and then we have e to the minus I n omega t, and then we integrate with respect to t. Okay, so the clear advantage of using the complex exponentials is that these integrals are very easy to evaluate. And so we have 1 over 2t, and then we just have to keep track of all of the minus signs correctly. So we have a minus 1 from the f of t, and then when we integrate, we get a 1 over minus I n omega, and then we have e to the minus I n omega t, evaluated from minus t to 0. And then when we do the second integral, we get a plus, and so let's see, we're going to get a 1 over minus I n omega. Then we have e to the minus I n omega t, and this is going to go between 0 and plus t. Okay, so let's just clean up some of this so that we can not get mixed up with our minus signs. So these minus signs will cancel. And so now what we just need to do is to put in the limits correctly. And so our Cn coefficients are 1 over 2t. And then let's see, we have 1 over I n omega. And then we have e to the 0, which is a 1, minus e to the minus I n omega t at minus t. So I think we get a plus I n omega times capital T. Okay. And then we have the second term. So we'll have a minus 1 over I n omega. And then putting in our limits, we have e to the minus I n omega t minus e to the 0. And so that's just a minus 1. Okay, so let's see what we have. We have 1 over 2t. We can factor out an I n omega, which is common to both terms. And then let's see, we have a 1, and then we have a minus 1. So overall, that's a plus 2. And then we have a minus e to the I n omega t, and a minus e to the minus I n omega t. So you might recognize this. E to the ix plus e to the minus ix is 2 times cosine of x, and so this should be minus 2 cosine of n omega t. Okay. So before going on, let's just recognize something else. Remember, the period is 2t, so 2t times omega is equal to 2t, and omega is 2 pi times the frequency, or 2 pi over the period, and the period is 2t. And so let's see, we get a 2 pi is what we are left with for omega t. 2 times omega t. Okay, so that's 2 pi. Or if we just had an omega t, that would be equal to pi. All right. So Cn is equal to 1 over, in this coefficient out front, we have a 2t omega, which we said is going to be 2 pi. So we have 2 pi I times n times 2 minus 2 cos of n omega t. Omega t is pi, so we get n times pi. So what we can do is we can cancel some factors of 2. And therefore, what we find, therefore our Fourier series coefficients are given by Cn is equal to 1 over I times n pi 1 minus cos of n pi. Okay. Now let's think of cos of n pi where n is an integer. If n is 1, we have cos of pi, which is minus 1. If n is 3, we have cos of 3 pi, which is minus 1. 5 would be cos of 5 pi is minus 1. So all the odd values of n, and odd results in cos of n pi equals minus 1. And then if we think of the even terms, it would be cos of 0 would be plus 1, cos of 2 pi would be plus 1, 4 pi would be plus 1. So our cos of n pi is equal to plus 1. So therefore, if n is integer, cos of n pi is equivalent to minus 1 to the n for integer values of n. Right? If we put in an odd integer, we'll get minus 1 as required, and if we put in an even integer or 0, we'll get plus 1 as required. So our Cn coefficients then become 1 over I n pi 1 minus 1 to the power n. And I think that's correct. So let's make a little table of what these values are. So we'll have n and Cn. And so there would be a bunch of numbers before this, but then what we could do is we could go minus 3. And so if we did minus 3, we would get, let's look inside the brackets first. 1 minus 1 would be 1 plus 1, so we'd get a 2. So we'd have a 2 over, let's see, I times 3 pi, so let's do 3 pi I, and there would be a minus sign because n is negative. Okay, and then we could do minus 2, but minus 1 raised to the minus 2 would be 1 over minus 1 squared, which would be plus 1. And in the brackets, we would get 1 minus 1, and so this would vanish. And so let's continue our table over here. NCN, and maybe I can squeeze one in here. So then we go to minus 1. Minus 1, we would get a 2 inside the brackets, a plus 2. So we would have 2, and then we'd have minus pi times I. So we'll put a minus sign here. We'll go pi times I, so it's 1 times pi. And then we would put in a 0. Minus 1 to the 0 is plus 1, and so we'd get 1 minus 1 is 0 in the brackets, so we'd get a 0. And then we'd have a plus 1. Plus 1 looks exactly like the minus 1 case, except for an overall negative sign. And so we would have 2 pi times I. Plus 2 would be a 0. All the even values of n lead to 0. And then plus 3 would look just like minus 3, except for the overall sign. And so this would be 2 over 3 pi times I. And we could keep going. Okay, so then if we were to actually write down this Fourier series, so let's remember, let's keep our coefficients here. So f of t was going to be equal to, let's just go look, it should just be the sum of Cn times e to the in omega t. Okay, so it would be the sum from minus infinity to infinity over n of Cn e to the in omega t. And so this would be equal, there would be a whole bunch of terms, and then let's start with the minus 3 one. So we would have c to the minus 3, which is minus 2 over 3 pi I e to the minus, n is 3, minus 3, so it's minus 3 I omega t. And then the minus 2 term would be just vanish, it would just be a 0. And then we have the minus 1 term, so we'd have minus 2 over pi times I e to the minus I omega t. Nothing for the 0 term, and then we'd have the plus 1 term. So we would have 2 over pi I e to the I omega t. Then we'd have the plus 3 term, 2 over 3 pi I e to the 3I omega t, and there'd be a bunch of other terms. Okay, so that's it. That's a valid solution for the Fourier series of the square wave in terms of the complex exponentials. I just want to take a moment to try to show that this is equivalent to what we had for the Fourier series in terms of sines and cosines. Okay, and so to do that, let's just make a note. Let's show that this result is equivalent to the previous Fourier series in terms of sines and cosines. So if you remember that Fourier series for the square wave, all the cosine terms were 0, so actually there were only sine terms left, and it was only the odd frequency sine terms. And so let's see how this works. So f of t is equal to, if you remember, for the cosine and sine version of the Fourier series, we had an overall prefactor of 4 over pi. So I'm just going to factor out a 4 over pi from all of the terms that we have. And I'll do a bit of rearranging here. So first, let's see, we're going to have 1/3. So let me start with this term. So we're going to have a 1/3. The pi out of the denominator has been factored out, and then we factored out a 4, so we're going to need to add in a 1/2, so that the 4 times the 1/2 is the 2, and then we still have an I, and I'm going to put a bracket here, and then we'll have e to the 3I omega t. Okay, and then I want to focus on this term. So the 1/3 is already out front. The pi we've taken out, there's a minus sign. We took out the 2, and the 4 times 1/2 handles this minus 2 that's out front if I got the minus sign inside, and so this would be e to the minus 3I omega t. Okay, and then we'll go plus. So I should say there would be other terms here that we're not dealing with. But so now let's think about the n equals plus 1 term. Okay, so we have to have a 1 over 2I out front. And then we would have an e to the I omega t. And that should be everything for that term. And then we have the n equals minus 1 term, which is exactly the same except for an overall minus sign and the fact that the exponential has a negative argument. So we'd have minus e to the minus I omega t. Okay, and then there would be more terms that we didn't write down. And so maybe you could start to see that this 1 over 2I e to the I omega t minus e to the minus I omega t, well, that's exactly sine omega t. And this 1 over 2I e to the 3I omega t minus e to the minus 3I omega t is exactly sine of 3 omega t. And so what we're left with then is that this f of t is equal to 4 over pi is out front, and then we'd have a bunch of terms, and we would have 1/3 of sine 3 omega t plus sine of omega t. In fact, actually, we wouldn't have these extra terms above, because all of the higher value of n terms would come before the n equals 3 and then the n equals 1. And if you look at this, this is exactly as we had previously. Okay, and so it's not a surprise that the Fourier series that we calculated in terms of complex exponential is equivalent to the one that we had previously calculated in terms of the sines and cosines. In this case, all the cosine terms were 0. So if we added more terms, there would be a 1/5 sine 5 omega t plus a 1/7 sine 7 omega t, and so on. Okay, so that's it. That's where I'm going to stop. The Fourier series in terms of complex exponentials is going to be useful when we do our derivation for the Fourier transform of a non-periodic function of time, up some kind of signal that pulses in time. So we'll make use of it there. Maybe just a couple of notes that we could make is that the exponential Fourier series is mathematically convenient because integrating the exponentials is always trivial, and we don't have a mixture of these sines and cosines with a separate infinite sum for each of those series. One consequence is that the series has kind of negative frequency terms and positive frequency terms. And so this is like the n equals plus 1 term. Here's the n equals plus 3 term. And so those would be kind of the positive frequency terms, because we have e to the plus I omega t and e to the plus 3 I omega t. Here's the n equals minus 3 term and the n equals minus 2 term. Sorry, that's the minus 1 term. And so these would be the negative frequency terms because we have e to the minus 3 I omega t and e to the minus I omega t. Okay, so we get negative frequencies in the series. So there's kind of a small consequence of having that mathematical convenience is the appearance of these negative frequencies in this series. And we'll see those negative frequencies also in the Fourier transform. Okay, good. Thank you very much, and we'll talk next time.